This is the Further Mechanics 2 paper from 2020. Let's just go straight into it. There's so much centre of mass on FM2. We'll start off with it. So we've got, of course, we're looking for the distance. It's quite an interesting question to give it some fairness. We're looking for the distance from the origin to the centre of mass, and we're looking to minimise that distance. So if you imagine the origin is here, we're looking to minimise the distance from it here, whatever's going on with these points here, which I haven't even labelled on. We're looking to minimise the distance. Of course, this is just Pythagoras, right? We're going to minimise x bar squared plus y bar squared square root. That's our aim. So of course we need to find x bar and y bar. We do that of course by doing some, I think of it as a weighted mean, right? Like you do this times this plus this times this plus this times this, and then you divide by the total mass. There you get this. You do the same for y bar, you divide by the total mass, you get this, and we can put those two things into here. Now at this point it's much more intelligent to realise that square roots are increasing functions, so when you get to here you can just minimise the distance by just minimising this quadratic here. I didn't think of that because I got distracted by the allure of writing dd by dp. So I set my sights on differentiating this. I did some numeracy here to make it a bit easier, but I set my sights on differentiating this just so that I could write this bad boy, and then set that to 0, which is of course a valid way of doing this, but definitely not the quickest way. You could of course say this to the power of a half, then you do some chain rule, half comes what brings down, times makes that a ninth, then you make that a minus a half, then you times by the derivative of this, which is this, I believe. I don't know why there's an 11 there, that's definitely a typo, isn't it? That should be a 16. That's just a typo, apologies. That should be a 16, and then you have a 16 plus 4p here. And when you set that to 0, the only bit of this that can actually be 0 is this thing here. Again, that should be a 16, but it doesn't really matter. This thing here needs to be 0, because of course this can't be. None of that can be. So it's just 16 plus 4p equals 0, and p equals minus 4. Much easier to just go back to here and find the minimum of this quadratic, or this quadratic, and you'll get p as minus 4. You can differentiate, you can complete the square, you can do whatever you want, but it's much easier than what I did. But at least I got to write down dd by dp, which is super fun. We have another centre of mass question here with x bar, y bar in it. We need to use the formulas here. So when you're doing an integral like this with a uniform plane that is made out of curve, to find y bar you do this integral, or two integrals really, this over this. Notice that this is just the total area. It's confusing because they give you the area r as this, and you read this and go, well, thank you, I could have worked that out. Like I could have just integrated this between this and this, and I'd have got that. But they're just being kind, right? Because they know that you need it for part of this formula here. You need to put it into there. So this 2.4 is just there, and then you do half of y squared. So we need to find y squared and halve it. This squared is 64 e to the minus 2x, because when you do a 2 out here, you just multiply, so it's minus 2x. We just put those limits in. We have a half to make 32. This I put in here, but again, I've mentioned this is just 2.4. So that just becomes 2.4. This you have to do properly, but it's not going to be too hard for the people watching this video, I'm sure. And we get this. Of course, here, just be a bit careful. You need to get rid of this minus 2 before you cancel the in the log. So put the minus 2 up to here to get 5 to the power minus 2, which is 1/25th, and then you can cancel this and this. Same thing over here. And we'll end up with some stuff, and we'll end up with eventually the answer of that. Good. And then next bit is, given that this is the thing, this is just this, but sort of actually made solid or whatever, we're going to hang it at C. And of course, when you hang something, it goes through the centre of mass, which is x bar, y bar, which means we need x bar. So the formula for x bar is this. It's slightly different to y bar, notice, and you just need to memorize those two formulas. But of course, we can do this again. This is just 2.4, isn't it? But x times y, so it's just x times this, which is this. You have to do an integral by parts here. So integrate e to the minus x, which is just minus e to the minus x, and do it again here to cancel this minus to make a plus, and then leave this one alone, and then differentiate it to just go away there. Of course, we can just substitute the limits in here, and we can integrate this from minus 8 e to the minus x, I guess. And then we could put the limits in. Did I even bother integrating that? Oh, of course, actually what you notice, yeah, that's nice. This is just 2.4 again, isn't it? This is just this. That's nice, that's just 2.4. Cool. And then you put the limits into this bit. Everything's sort of, you can, I'm sure, you just need to move this minus 1 out of the way, like we did before, to make a fifth. And then stuff cancels, and then you get down to this, which is this. You just type it in, you get this. So the centre of mass here, I've just kind of randomly put it in the shape here, is at 1.08, 1.4. And of course we can do, we're looking for this at this angle here, between CB and the vertical, which is always the line going through the center of mass. And of course we can do a bit of trig here. This distance here, now C to B, I think I worked out, if you put in log 5 into here, you get, this is 1.6. You could just type that into a calculator, put log 5 into that. Or you can just notice, put the minus at the front, it's log 1/5. E and log cancel, it's just 8 times a fifth, which is 1.6. So that's 1.6. And then I can just do 1.6 minus 1.4 to find a little distance here of 0.2. And then this length here, I think, is log 5 minus the distance 2x here across here. So it's 1.5 minus 1.08, I believe, which I think is this. So log 5 is all of that. And then 1.08 is to the center of mass. So it's just log 5 minus 1.08, which is that. And then I can just do tan inverse of opposite over adjacent. And I'll find my angle of 69, which is nice. Question number 3. We have a particle, first non-center of mass question, I guess. So we have F equals ma. We're looking for x, which means we should be using this form of F equals ma. There are 3 forms of F equals ma you need to know. Of course, F equals ma, F equals mv dv by dx, in case you're looking for something in terms of x, and F equals m dv by dt, in case you're looking for something in terms of t. So those are the only 3 things you need to know. We'll do the last one down here as well. But here, let's just start with this then. So we've got mass of this, that's useful. We've got a force of this, and that's directed towards O, so that's directed backwards to where it's currently moving, so that's why there's a negative there. That's the mass, that's the velocity, dv by dx. This is just a separable differential equation, so divide by v squared, and then times everything by 2. I don't know what's happened to the minus here. What on earth has happened to the minus here? I don't know. Answers on a postcard, please. It's magically reappeared again. Amazing. So there should be a minus here, and then it just, and then it should be here as well, which it is, which is good. We could just integrate both sides here to get this. With a plus c here, we've got some initial conditions. In fact, we've got 2 of them. When x is 1, v is 4, so we'll put those in. We'll get this. When x is 2, v is 2, we'll get this. I can't remember what I did here. What did I do? I did this one, it looks like, minus this one. C's cancel. This minus this. This minus that, of course, is plus, so we get this. Divide by 2. Of course, 4 is 2 squared. Bring the 2 out to the front. And then 2 log 2 minus log 2 is just log 2. Divide by 2 and we get k as that. Which we can then substitute back into here to find c, I believe, is probably what I've done. Good, that cancels. That's again just 2 log 2. Add it to both, or take it away from both sides, we get this. And so I think our integral is that. We're adjusting for the c and the k. Which I do need to rearrange to be in the, I need to make v the subject. So add this to both sides, I guess. There are probably easier ways of doing this. I think I could have done less work. Raise both sides to the power e. This is, of course, this thing times this thing, because we add exponentials when we're doing this. I've been quite fancy here, haven't I? I've done 3 times log 2 and then immediately put the 3 at the top there. So I can cancel this for an 8, because 2 cubed is an 8. And then this is fine, I guess. We get this. You can bring the x out as well. That's also super fancy. The minus goes over here to make a 2 to the minus 1, which is a half. E and log cancel, so this just becomes a half. And you get this, and so a is 8 and b is a half will be our final answers. I'm sure there are much easier ways of doing that, but I can't be bothered to know exactly what they are right now. The time taken, so I mentioned this earlier, but when you're looking for time, you don't want to use the form of f equals ma that we used. We want to use this form of f equals ma, because it's got time in it, which is good. So we just continue with the same thing we did before. This one's actually easier, I think, because the equations sort of, like, this integral is super easy, isn't it? So yeah, this is super easy to integrate. We'll just integrate this for t. This becomes, well, this is v to the minus 2, so it's minus v to the minus 1, plus c, of course. And then, of course, k is a half log 2. We saw that in a previous slide. 2 times a half cancels, we get this. I think I times everything by minus 1 in order to, I don't know what I did there. Cool, this is correct though, because the c doesn't matter just yet. We'll find out what the c is, I guess. In fact, will we? I don't think we will. When v is 4, I can just find what t value that gives me. T is this, it's a quarter plus c over log 2, and when v is 2, I get this. And then, of course, if that's the time when v is 4 and that's the time when v is 2, I can just do this, take away this to get the time in between them. the time taken for it to get to there, so I can just exactly read that. If this looks weird, it's because I could have just integrated. When I did this integral here, I could have just done a definite integral between 4 and 2, which is of course would make the c's cancel, and you just get this anyway, but for some reason I decided not to do that. I can't remember why, because I made this a while ago, and I'm recording a little bit late. But anyway, so who knows what past R2 Drew 2 was thinking at that time. So we have a cylinder here, and we're being asked, again, the 3rd out of 4 questions to be asking us about centre of mass. Amazing. So let's deal with the centre of mass of the cylinder first, and then we'll deal with the sphere on top. So the centre of mass of the cylinder is clearly just going to be 2/3 the way up, 2/3 r of the way up, so that's really boring. The centre of mass of this hemisphere, the formula book helps you out here. It's 3/8 of r, so that's going to be 3/8 of r above this flat plane here. 3/8 of r plus 4/3 of r gives you this. So that's the distance from down here. And now we just do that kind of weighted, adjusted mean thing that we always do, considering the volumes instead of the masses. So the volume of the hemisphere is, normally it's 4/3 pi r cubed, but it's a hemisphere, so it's 2/3 pi r cubed. The volume of the cylinder is just pi r squared times the height, which is this, and we get this. And so the distance to the centre of mass is going to be this distance times this volume, plus this distance times this volume, divided by the total volume, which I think is what I've got there. Of course, lots of things cancel, which is nice. I'm not going to bore you with the numbers here. You get this, which is nice. Good, and we have our answer. Kind of an interesting second part to this, though. So the volume of the whole thing is 2 pi r cubed, so I've just left that there. We're on a sort of a flat surface here, and we have our shape here with the centre of mass there. Now the total height of it is 7/3 r, because it's 4/3 r plus r, which is that. And from that 7/3 r, we're pushing across with some force P. And now this has a mass downwards of, just call it mg, which means it's got a reaction force of r, and then the frictional force going this way is going to be mu r, which is just mu mg. And we're told that this thing is going to slide along before it starts tilting over. So if you imagine this plane was like super, super rough, this would tip before it slides. Apparently that's not the case. Apparently this is kind of smooth enough such that when you increase this force, it moves along before it will tip over. And it just wants us to give us a range of mu values for which that happens. So we need to consider two things here. We need to consider, of course, if it's sliding along, that means P is beating mu mg. So it's sliding if P is greater than mu mg. So that's the first obvious thing we can write. Now, what about the tilting business? Well, focusing on this point here, because of course that's where it's going to tilt from. If it tilts over, it's going to start turning on this point down there. Take moments from this point here. Now, from 7/3 r away, you have a force of P tilting it clockwise. And from r, remember the circle on the bottom here has radius r, from r away you have a force of mg tilting it anti-clockwise. So it's on the point of tipping if that force tilting clockwise, 7/3 r, or that moment I should say, 7/3 r times p, is equal to r times mg, the force going anti-clockwise. So of course we could just cancel the r's, cancel whatever else, nothing else actually, times by 3 divided by 7, and we get this. And now we know it's not tipping, right? So we can say we need P to be slightly less than that for it not to tip. But of course, what we really want to say is that we want this to happen before this. And for that to happen, like if mu was 0.9, you would need P to be bigger than 0.9 mg for it to slide. But you need P to be less than this for it not to tip. So that can't be the case. So we just need mu to be stuff less than 3/7. Right? If mu is just less than 3/7, it will start sliding before it starts tipping, which is exactly what we want. Of course, mu also needs to be greater than 0 because that's how mu is defined, and we'll end up with our range there. Question number 5 then, this is should have been animated in, but we'll get to it, I guess, when we get to it. So we'll just leave it there for now. We've got this thing is being spun around the floor in a circular motion like this. 60 is remaining constant there, 40 remaining constant there. So there's going to be a tension in this string here. In fact, that's the first thing we're being asked to find. This has a mass 0.75, so it's going to have mg going downwards of 0.75 g, there's going to be a reaction force with the floor that you're spinning this on. So we'll put a reaction force there. It's a smooth floor, so no friction to worry about. We've got an acceleration, well, actually we've maybe first say we've got a distance here of just, never work in centimeters, obviously. This is 0.6 meters, this is 0.4 meters. 0.6 squared minus 0.4 squared square rooted is this, apparently. So that's as it's there. And now our acceleration going towards the center, usually we use v squared over r, where v is just the velocity, but we've been given angular velocity here, or angular speed. And the formula for the acceleration towards the center for that is just r angular speed squared. So the r, the radius of the circle that it's going around in, is this. So it's just this times 3 squared is our acceleration towards the center. And I think that's basically everything you need. Oh no, one more thing is this angle here, which is of course just sine of 40 over 60, or 0.4 over 0.6, which is this in radians, because of course we're in radians. So that's that. And now I think we have enough to be going on with. Vertically speaking, we have t. This is going to be t sine 0.73, isn't it, going upwards? So t sine 0.73 plus r equals 0.75 g. That's just resolving forces vertically. But also horizontally, we have an F equals ma formula, because we have the acceleration here. We have a force going across of t cos this, and that's it. So I think we're just going to have t cos this equals m, which is 0.75, times this acceleration towards the center. Of course, from here we can work out t. Just type it all into a calculator, and then we can shove that t into here, and we can work out r. And we'll have those 7 marks done. The angular speed is now gradually increased. When do we lose contact with the table? Well, we lose contact with the table when the reaction force is 0, clearly. So r is 0 now, is what we'll say. And now that just means that t sine of this angle here is going to be equal to mg, because there's no r anymore. So that'll give us a new t. We'll type that in. We'll get roughly 11. And now if we know that, this acceleration towards the center no longer applies, because we've increased the angular speed. So, but what we can do is we can set up F equals ma again horizontally, because we have t cos this with this new t value equals m times the acceleration towards the center. M being that. Of course, pour that in, you get a as this. And then we can use that same formula, which is r times omega squared, where this is, we can use a equals r times omega squared, where that's a, and r is obviously this. So we can solve for omega, so a is that, r is this, and then I square rooted at the end to find omega, and that's the answer to the question. Question 6 then, another circular motion question, although it's slightly different because it's going around a vertical plane rather than horizontal. So we'll give it to them. This is a slightly different question. Show that tension in the string is this. So firstly, you've got tension there, and we've got a few other things going on. So this distance here, well, that length is L, and this is opposite the angle, so this is going to be L sine alpha, which is going to be very relevant. We can set up, according to the energy conservation idea, initially we have speed of this. So this is our initial kinetic energy, half mu squared. But we also have potential energy originally of mgh, where this is h. So I'm sort of setting this line here to be 0 potential energy. So this is the increased height that we have originally that we don't have anymore. And that just equals the only energy that we have left, which is a half mv squared, where v is the new speed. This is an inextensible string, so there's no energy stored in the spring or anything like that, according to this. So that's the energy equation. We also have more things going on here. We have an mg going straight down from this particle, and that means we have a component this way of mg sine alpha. Now, the way that I worked out was a bit annoying. I said if you go across here, that's alpha, and now this is mg here. This is alpha here. It's going across here, this is alpha, which means this is 90 minus alpha, which means this length is mg, it's next to the angle, so that's mg cos of 90 minus alpha, but cos 90 minus alpha is the same as sinus alpha, so we'll get sine of alpha there. There are probably other better ways of thinking about that, but I've got it like that. And now we can think F equals ma from here. We've got an acceleration towards the center. This time we haven't been given angular speed, but actual speed, so we're going to use v squared over length, v squared over r, for our acceleration towards the center, so that's v squared over L in this case, and that's just ma, so this is F, or so it's t minus this equals ma, and so of course we could rearrange this for v squared, and then we can shove that v squared into here. And I think if we do that and everything works out quite nicely, we'll end up with exactly what they wanted us to get. Now find, in terms of g, now the speed in which the string goes slack. So if string goes slack, that means tension is 0. So okay, what we're going to do is we're going to set t to be 0 here. And if you do that, so just move this thing over, you end up with lots of things cancelling, and then sine alpha equals minus 3/5. And all we have to do then, we're looking for the speed when the string goes slack. We can just shove that sine alpha into here, because look at this. The only thing we don't know here is v. So let's just put that sine alpha into there, minus 3/5 into there, and then let's just, I've also doubled everything just to get rid of those halves. And let's just sort this out. We end up with v squared equals, or v equals this, which is good, so that's our 3 marks. Now find, in terms of L, the greatest vertical height reached. Now what's going to happen is this is going to go round, and at some point the string is going to break. And so we need to know the height at which the string breaks, but then we also need to know, because as soon as the string breaks, it's going to sort of, sorry, as soon as it goes slack, I should be saying, as soon as it goes slack, so it's going to come around here probably, and then it's going to go slack, and it's going to fall off of this circle, so it's going to come around here, go slack, and sort of fall off the circle like this, and kind of go towards the center. But of course, the moment it goes slack, it's just following basic kind of laws of motion, so we're going to have to do some suva after we do that. So let's get to it. So let's have, firstly, we know sine of alpha was minus 3/5. We could just work out alpha. So do sine inverse of that in the calculator. That's probably not that helpful. Let's find some other values. So I did 180 plus this to get this, and then 360 minus it to get that. And this is going to be the one where it goes slack. It goes around 216 degrees, somewhere over here, where 180 minus that is this. So this is going to be the angle. And what I want to know first, I want to know this distance, because that's going to be our initial height before it just starts slacking off and following regular kind of ideas of motion. So what's this distance here? Well, this is just L, of course, as we've seen before. So this is just L sine 36.9, which is actually just 3/5 L. It's just the 3/5 from here by definition, actually. So that's the 3/5 L. Now the particle is it's traveling at this speed. We worked that out before, didn't we? It's traveling at this speed when the string goes slack in this direction. So let's do some components here. Let's work out, well, here, if this is 36.9, let's just call it theta. That's the right angle there. That's 90 minus theta. That's 90, which means this is theta, which means this is v cos theta, because it's next to the angle. So that's v cos of this. Cos of this is just going to be 4/5, by the way. So it's going to be 4/5 of that. So that's my vertical component of my speed. And now I can just do suvat if I break out, if I look at the formula book here. What's the thing that I know nothing about? Well, I think I know nothing about t. So this looks like a useful formula. It's going to follow regular laws of motion. And what I want to know is, when is its vertical component of its velocity 0? When is it not going up anymore? When is its vertical component 0? So when is this v 0? This u will be this here. And then 2 times a is obviously g, minus because it's going downwards, and s is the distance that it's going to go vertically at that moment. So let's use this formula here with v0, u this, and an a being minus g. We'll find out s is this, and then of course that's the vertical distance it travels before it's going horizontal and then therefore coming back down again. So we're just going to do this plus this, and that'll be our answer for the greatest vertical height above this level O. And yeah, so that's good. Last question then is about simple harmonic motion. We get 7 marks for doing the easiest part of the question, which is good. We just need to show that it's simple harmonic motion. So as soon as I see these, I write down the T and the E formula for elastic springs. I hope I've got this right, actually. It didn't end up not using this one, but anyway, this one we'll use. So we've got, I always draw it like this. We've got sort of a ceiling with the spring here with M at the end of it. There's definitely going to be tension in the spring. There's definitely going to be mg going downwards. And now, what I want to know first, it's told it's going to be pulled down 7/4 L, but I don't really care about that for now. What I care about is where it sits at equilibrium, because that's going to be important to my simple harmonic motion. So let's work out where this is at equilibrium. So obviously t minus mg equals ma, but a ends up being 0, so we just need t equals mg. But t is this here, right? So we can put that in with lambda being this, and we can work out that the extension at equilibrium is 1/4 of L. So this is going to have length L here, and then another 1/4 of L, and that's it sitting at equilibrium. Then it's going to be pulled down. Now, if it's sitting nicely at 1 1/4 L, that's 5/4 L, it's going to be pulled down another 1/2 L. which again isn't amazingly important, but it's going to be pulled down under the half L. Now the reason I needed the quarter L so much is because when we have this, so it's being pulled down, the tension now is going to be at any random point x that it's at. This x is the displacement from this equilibrium point that the simple harmonic motion is working in, and the simple harmonic motion is going to work with equilibrium point, that 5/4 L that we found, which is a quarter L beyond just the natural length L. So we'll use the quarter L as our center point for the equilibrium, for the simple harmonic motion, and then x is just the distance that we're away from that center point. So that's going to be our tension, and now we can just do F equals ma again, where a is given as x double dot, and if we plug all that in, so this minus this equals m times this, this and this cancel. I've expanded this out, which just cancels there and then puts a 4 there. This and this cancels, which is excellent, so we get this, the m's all cancel, and then we have, this is obviously of the form minus omega squared, x equals x double dot, so this is simple harmonic motion with omega equaling that. The period we can just get by doing, the period is 2 pi over omega, that's just the standard formula, so we'll just shove in omega into there. Of course, root 4 is 2, so you can bring that aside and cancel these, and you just get this. So that's good as well, we've done that bit then. Now find the maximum kinetic energy. Now simple harmonic motion is when you go up and down like this, but the point is your fastest velocity is in the middle when you're at the equilibrium point. It's fastest right in the middle. And that's of course when you're going to have maximum kinetic energy, when you're fastest. So we're going to be fastest in the middle, which means x is 0. Represents the displacement from the equilibrium point of the simple harmonic motion. So we're going to say x is 0, and this is the formula that you get given. Well, you don't actually get given it. It's in the textbook. It's not in the formula sheet. So you need to know this formula. But of course, we've just argued x needs to be 0. The displacement from the center needs to be 0 for maximum velocity and maximum kinetic energy. So that's 0. You get v squared equals a squared omega squared, which just means v equals a omega, because we obviously don't care about any negatives here. And a is the amplitude, which is well, it sits at 5/4 L. So the amplitude is a half L, right, to get it down to 7/4 L. So I said that wasn't important, but it is now. So A is a half L from there, so that's the amplitude. Omega we already know is this. So we just times those together, we get V max. And so maximum kinetic energy is going to be a half m times this squared. And you just kind of sort that out and you eventually end up with this. And that's our maximum kinetic energy. Lastly, find the time for which each time within each oscillation for which the length of the spring is less than L. So the way that I thought about this is it's currently 7/4 L, which means it needs to travel 3/4 L to become less than L. But of course, when we're using this formula here, sorry, that's the formula that we've got. When we're using this formula here, which is the formula for how long something takes when you start on the end point, again, this isn't given to you, but so you just need to know it. X, again, remember, represents the distance from the center or the equilibrium point. So I need x to be upwards minus a quarter L. And the reason I need that is because currently it's a half L stretched downwards, but I don't really care about that. I need it to go all the way along there, that half L. I then need it to go another quarter L, that distance that we found that it was naturally stretched at, and then it will become length L. So I need x, the distance from the center. The center is 5/4 L down. I need it to be a quarter L upwards, which is minus a quarter L. Because it's upwards, it's minus a quarter L. A is a half L, as we discussed. Omega is that, and so on. We can solve this for t. Eventually you get cos inverse of that is that. Eventually you get this for t. And now my argument was, okay, that's how long it takes to get from all the way down here up to the point where the spring is length L. But because simple harmonic motion is like symmetrical, it's nice, right? All I have to do now is do the total period, which is this, which is that's how long it takes to do this, then this. I just need to do this minus this time it took to get from there to there, minus this time again, which is how long it's going to take to get from there, when it goes back up and down again, back to there. So I just need to do the period minus 2 lots of this. This represents how long it takes to get from here to here, which means it also represents how long it takes to get from here to here. So that I can just do the period minus this again, and I'll find the time it takes to do this bit, going up and down up at the top here. So this minus this, of course, that's 2/3, which makes this minus that 1/3 of pi, and we end up with our total time being that.